Okay, taking a look at example 3, we're going on to a different format here. This is a very common format. This would be the sign substitution. So here, we'll let x equal 4 sine of theta. So dx is 4 cosine theta d theta. This is also a definite integral. So what we can do here is take this substitution equation x equals, solve it for theta, which forms a function of x. So theta, a function of x, is the arc sine or sine inverse of x over 4. So then theta of 0 is the sine inverse of 0. Sine inverse of 0 is 0. And then theta of 2 root 3 is the sine inverse of root 3 over 2, it seems. So now remember, sine inverse, it's a function that only spits out angles on the right half of the unit circle, so from negative pi over 2 to pi over 2. So sine is the y value, so our y value is root 3 over 2. So it's going to be, well, this is not drawn to scale. That's a 45-degree angle. Really, if drawn to scale, it would be a little bit more like that. This would be right here, this point. So this is an angle of pi over 3. This is pi over 3. Okay. So got all that taken care of. So now we should be able to say that this is equal to, I'm just kind of sectioning that off, that scrap work. This would be equal to the integral from 0 to pi over 3. And then x cubed, so we're going to have 4 cubed, which is, I believe, 64. So this is 64 sine cubed theta. Downstairs, this is the square root of 16 minus 16 sine squared theta. And then dx is 4 cosine theta d theta. And that looks like just about everything. Let's go ahead and remind ourselves that this term in the bottom turns into the square root of 16 cosine squared theta, which is just 4 cosine theta, which cancels the 4 cosine theta there. Ooh, so that's a lot of cancellation and stuff right there. So again, let's recap here. The inside of the square root turns into a 16 cosine squared theta. That's a perfect square, so that turns into a 4 cosine theta, and then that will cancel with the 4 cosine theta in the numerator. So what's left over here is a constant of 64, and then a sine cubed theta d theta. So for this one, what we can do to solve it, this is definitely of the form of a section 7.2 problem, just what happens when you've got sines and cosines raised to different powers all multiplied together. In this case, we would go ahead and let's see, I would break off one of the sines and then rewrite this sine squared as a 1 minus cosine squared theta. And then I would do a substitution. Let u equal cosine theta, so that du is minus sine theta d theta. So we'll swap out the sine theta d theta for a negative du. So this would become negative 64. We have to change our bounds. All right, so then u of 0, we've got what's going to be cosine of 0, which is 1, And then u of pi over 3 will be the cosine of pi over 3, which is, what's that going to be? Cosine of pi over 3 is 1/2. So this would be from 1 to 1/2. And then this would be 1 minus u squared. And then the sine theta d theta becomes our negative du. Now this negative out in front, I can absorb it into the integral to swap the order of the bounds, since they are sort of the opposite orientation. So I can do that. So swap that. So this would be 1/2 to 1. So from there, we can actually pretty much finish this up. 64 times the quantity u minus 1/3 u cubed between 1/2 and 1. 64. This would be 1 minus 1/3 minus 1/2 minus minus, so plus 1/3 times 1/2 cubed, so 1/8. And so this is 40/3. Notice that since this was a definite integral, unlike the previous example where we needed to draw the triangle in order to go back to the original variable using our trig substitution, if we're doing a definite integral, as long as you change your bounds at each substitution that you make, so once for the trig sub here, and then again when we did the u sub, if you change your bounds each and every time, then there's no need to go back and back substitute. That's why I'm a huge proponent of changing your bounds. I know some people were taught not to do that. I honestly think in virtually all circumstances, I feel like not changing your bounds and going back to the original variable before plugging in is equal to or more work than what you would otherwise do. So